I thought that I might do some properties of the integrals that we spent a lot of time doing all those limits. I thought some visual stuff might be nice. So let me just draw a rough sketch of a graph. And let's say we have a function. Let's call it f. And from a to b, if the function is above the x-axis, then we were interested in finding that area underneath of the graph, but above the x-axis and between a and b. And this, of course, the area underneath of that curve is equal to the value of the integral from a to b, f of x dx. Now I think we saw this when I was doing one of those examples. One of the last examples had a function that was negative throughout the whole time. And that's true if, say, you have an interval from a to b and you have a function that is strictly negative down there. You still have area enclosed in the graph, but now it's below the x-axis. And let's say, just give it a different name, g. Then negative a equals the integral from a to b of g of x dx. That's because when you do those summations, all of the rectangles are upside down, so all the rectangles have a negative height. And so when you do all those computations where you do width times height, well, the heights are negative for all of them. So you can pull out the negatives in front of an integral or in front of limits. And so that shouldn't be any surprise that when you drop below, it measures what I like to call negative area. Most of the properties we're going to deal with here are going to be pictures, are going to come from pictures, because I think they're fairly obvious in that case. Suppose, once again, every function I'm dealing with here, unless I say otherwise, is a continuous function. I don't want to deal with anything else just yet. So let me go ahead and grab another function. I'll call it f again. And suppose that you have an extra number c that's in between here. Well, you should know that when you look at the area of anything, you can break it up into any kind of pieces you want. And you would know that the area between from here to here, so let me go ahead and take out a thing here so I can put, let's call this one A1 and then this one A2. Well, A1, that equals the integral from A to C of f of x dx, and A2 equals the integral from C to B f of x dx. And I don't think it's takes too much of the imagination that if I didn't have this split here at all, that if I were to take this A plus this A, that it should add up to the area underneath of the whole curve from A to B, and that is indeed what's true. If I go from A to B of f of x dx, that's going to equal A to C f of x dx plus the integral from C to B f of x dx. With that in mind, then, if you have some sort of of a function that does things like this, and let's say it starts at A, ends at B, and just to help me out here, I'm going to put C is where the beginning of the negative part is, and D will be the ending of the negative part. So we have A1 will be this area, A2 will be that part, and then A3 will be the last of these areas. And now, using what I just spoke of a minute ago, the integral from A to B of f of x dx is going to equal the integral from A to C f of x dx plus the integral from C to D f of x dx plus the integral from D to B f of x dx. And you can see then that this from A to C, that will be A1, but from C to D, that'll be minus A2, but from D to B, that'll be positive A3. So as an example of that, compute the integral from 1 to 4 of x minus 2 dx. Now, since we do not have formulas for anything, and I don't mention Riemann sums or anything like that, so I don't intend for you to do this using Riemann sums, the expectation is that this function will be simple to look at as a graph, and it is. It's a straight line. So what we have then is the line f of x equals x minus 2 will have a y-intercept of 2. We'll also have an x-intercept of 2. Straight line. And let's see, then when we get to 4, when x is 4, 4 minus 2 is 2. Perhaps I probably should have put that closer over here. So the interval, and then when I put in 1, the height of that is negative 1. So what I'm looking for is this down here would be like A1, and then this in here would be A2. So A1 equals, this is a triangle of height and base length 1, so it's 1/2 times base times height, but I forgot the negative already. Since it's below the x-axis, you got to have the negative there. No, go back here. I'm getting ahead of myself. That equals 1/2. A2 equals, it's also a triangle, and the base is 2, and the height, well, the height is also 2. So it's 1/2 times base times height, which is equal to 2. So then the integral from 1 to 4 of x minus 2 dx equals negative A1 plus A2. So that's negative 1/2 plus 2, which equals 3/2. So most of the integrals we're going to be evaluating will be because you'll be able to look at a graph and get the information from that because of common formulas that you have. Okay, consider the integral from 0 to 1 of the square root of 1 minus x squared dx. Well, you ought to know that f of x equals the square root of 1 minus x squared is the top half of a circle of radius 1. So with that in mind then, a picture that I would have would be something like this. Let me draw maybe the circle part first. See how good I can get it looking. And then I'll draw my axes. So there's the graph of f of x. Now, and it starts at -1 and it ends at 1. I want the area from 0 to 1. So this is what I'm looking for. So it's 1/4 of a circle. So the integral from 0 to 1 of the square root of 1 minus x squared dx equals 1/4 of a circle. What's the area of a circle? It's pi r squared. The radius in this case was 1. So this equals pi over 4. How about the integral from -2 to 4 of just the number 5 dx? Well, that's easy enough to draw. 5 comes through like a horizontal line, is a horizontal line. And if I go from -2 to 4, I can make, it is a rectangle. In fact, if it's a rectangle, it's really easy. The base is 6 and the height is 5. So that equals 6 times 5. That equals 30. I thought I might sneak in, not sneak in really, but use some of my old test questions and see how it goes. Here I have the graph of a function is given. The function is a series of semicircles. Okay, so semicircle, semicircle, semicircle. Gotcha. I want the area or the integral from -3 to 5. So let me first mark off -3 to 5. Alright, so what do I have here? I'm going to have this little quarter circle, then I'm going to have this whole circle, and then I'm going to have another quarter circle up here, whole circle, half of a circle. So let me get these areas. The area of the first piece, I don't know if you can see it, but -3/4, it has a radius of 1, so it's 1/4 times pi times 1 squared. And then this piece here, the radius is 2, and I have half of a circle, so I have 1/2 times pi times r squared. And then here I've got a quarter circle again, but the radius this time is 3, so I have 1/4 times pi times r squared. So the integral from -3 to 5 f of x dx equals pi over 4 minus, this will end up being 2 pi, and then this will end up being 9 pi over 4. And, well, I can add pi over 4 and 9 pi over 4. It gives us 10 pi over 4 minus, now 2 pi can be thought of as 8 pi over 4. So I'll end up with 2 pi over 4, and that'll end up being pi over 2 for the answer. The next property goes like this. Let c be a constant. Then if I have the integral from a to b of c times f of x dx, I'm able to factor the c in front of the integral and get c times the integral from a to b f of x dx. And this shouldn't surprise you at all. Anytime the reasoning goes like this: if the integral is the limit as n goes to infinity of I equals 1 to n f of x sub I delta x, well, if I had a c in front of this, right, then you can factor a c in front of the summation because it's a common factor to all the terms in the sum. But then you can also factor the c in front of the limit because that's one of the rules of limits. So this equals c times the limit as n goes to infinity, summation I equals 1 to n f of xi delta x. As an example to illustrate that, suppose I give you the integral from negative 5 to 5, 7 times the square root of 25 minus x squared dx. Well, that equals 7 times the integral from negative 5 to 5, square root of 25 minus x squared dx. Now, we're actually expecting you to know what this integral is. This here is the top half of a circle centered at the origin of radius 5. So, since it's a circle of radius 5, I don't even need that thing. I think you can figure it out when I do 7 times. Circle of radius 5, I got 1/2 times pi times r squared. So 25 times 7 is 175. We have 175 over 2 times pi. A couple other rules that are from the definition. Call it DEF, or definitions. If I try to integrate from beginning and end starting at the same place, that's going to equal 0. Basically, think about it. If you go from a to a, the thickness of the interval there's no thickness. It's 0. If you think of it as a rectangle, it has 0 width. So I can't even get started on having Riemann sums. I can't even begin it. And then another one, which will make sense the farther along you go, is that if I go from a to b, that's the negative of reversing from b to a. Here is another test question. And what I have here is I'm giving you the values of various definite integrals, and from these you're to calculate other values of definite integrals. So let me go ahead and start with f of x, part A. The integral from a to c of f of x dx. Well, since I have an a to b and then a b to c, I can rewrite this as the integral from a to b, f of x dx, plus the integral from b to c, f of x dx. And let's just see if those numbers are there. So let me see, is a to b there? A to b is -1. And then is b to c there? Yes. B to c is 49. So this equals 48. Part B, this is the integral from b to a of f of x. So it's just the negative of the one that is a to b. So it'll be the negative of -1, which will equal 1. Part C, I have no idea what this is asking, but it should just, you can add these together and just make it 5 times g of x. I think that'll be easier. So part C, we're doing the integral from a to c of 5 times g of x dx. And do I have any that are from a to c? No, I don't. So I'm going to have to do a little more work even when I do break this up, or take the 5 out. So I'll do that. I'll take the 5 out front times the integral from a to c, of g of x dx. So then I'm going to have to break it from a to b and then from b to c. So I have 5 times the integral from a to b, g of x dx, plus the integral from b to c, g of x dx. Let's see, what was a to b equal to? That was 3, and then b to c was e. So I have 5 times 3 plus e. And you can leave it like that's fine. I don't need anything else. And then finally d was b to a, g of x minus 5 f of x. So we're going from b to a, g of x minus 5 f of x. G of x minus 5 f of x dx. And once again, because of the limits, the properties of limits, you can break up sums and subtractions in integrals. So I can rewrite this as the integral from b to a of g of x dx minus, and at the same time I can pull the 5 in front of the f of x, b to a f of x dx. And I saw in both cases I did not give you a b to a, so I'm going to flip these, and I'm going to enter negative the integral from a to b, g of x dx, plus 5 times the integral from a to b, f of x dx. That equals, now what was g? G was from a to b, I think was 3, okay, and then f was negative 1. So I have negative 3 plus 5 times negative 1, which ends up equaling negative 8. On an exam, it's not uncommon for me to ask you to evaluate, or at least write, a certain limit of Riemann sums as an integral. So, what are we going to do here? We want to write this as the integral from something to something, and if you want, we can have dx all the way over here. So, what I need to know is, what are the values of x? What is the length of the interval? Where does it start? Where does it end? And let's take a look. One thing I've told students often is you can always find your dx here at the end. So you know when you're doing the sum, this part here, pi over n is delta x. So delta x equals pi over n. That means the length of the interval is pi. And you remember, if this is supposed to equal b minus a over n. So it depends on where it starts and ends. And inside of here, you have some possibilities. I typically would let x be as simple as possible. This guy right here, pi over nk, is going to be x sub k. It's going to equal pi over nk. Now, here's how you can tell where to start and where to end your interval. Start. Do you remember? Start is when x is 0. That was x0, not x6, but x sub 0. So I can start it at 0. Well, if the length of the interval has got to be pi, then it ends at pi. But if you really want to know for sure, it ends at xn, which is pi over n times n, which equals pi. Okay, now I've got the square root. I have a 1 plus x, and there you have it. We will have ways of evaluating this thing by the time you take this test, but you'll be required to recognize this limit, or the limit of Riemann sums. You'll have to recognize it being put back into an integral form, and this happened to be the case of right-hand limits, which is probably what I'll normally do with them, but maybe to be sneaky or something, I could throw in left-hand limits. It's very unlikely I would do midpoints. They're just needlessly complicated. Another example is, can you compute the integral from 0 to 2 pi of sine of x dx? Well, if you look at the graph of sine of x, it starts, I've often heard students tell me it starts down, where cosine starts up. Whatever you have to do to remember is fine with me. Then it comes and goes like this, and there's 2 pi. Well, you ought to know from symmetry that if that area is A, this area down here is also A. So what happens to the two of them? Well, this A cancels with that A, and you end up with 0. What about something like this? The integral from 0 to pi of tangent of x dx. Well, let's take a look. I know that pi of 0 is 0. I know that pi comes in and goes like this. But then we have a vertical asymptote at pi over 2. And then down here, we come up and it's 0 again at pi. So how do we do something like this? Well, the answer to this is does not exist. The reason why is if you try to come up with any partition of this interval, say you have a partition that is right before and right after pi over 2, and suppose you chose to use the midpoint for some reason. Well, how tall are you going to make this rectangle? I mean, or which way are you even going to do it? Are you going to do half up and half below? There's no way of doing it. You'll have an infinite-sized rectangle. So because the function is unbounded, tangent of x is unbounded, in that interval. Because of that, you can't even start the process of having a Riemann sum to begin with.